In this session, we will analyze some data using redundancy analysis or redundancy discriminant analysis using R. So you should fire up the script, and the first thing you do is set your working directory. So I don't discuss this in detail anymore. The first part of the script is always related to that. We will use some data set that comes with the package Wiggen. We load the Wiggen library first, and then we load the legend data. We have a look at the data. This is basically data from legends that have been collected in 24 sites, and if you want to know more, you can use the help function to know more about this species that have been collected. When we look at the top of the data, we see that many species have been found. The abundances or the fraction of abundances, they vary between the different species. That needs to be taken into account. Here we look into the help file, and we see that if we would be interested into more details of the data, we could consider reading this paper that will provide us with more information. We are not interested in more details here, and we just go for demonstration purpose through this analysis. One question is, if we want to find a relationship between explanatory variables and the species, then we could strengthen this relationship by removing very rare species. For example, if we use a technique such as RDA that relates a linear gradients to species occurrence or abundances, then it's obviously more or less impossible to relate a linear gradient to a species that already occurs once or twice in a site, because then you have generally no gradient in the species occurrence. So the removal of rare species has been discussed in literature, and I refer you to the papers that are cited here if you want to look into more details. We remove all species that occur in less than 4 of the 24, 4 or less of the 24 sites. We do this by first calculating the sum of species occurrence. So what we do is we use the decostand function that is for standardization of data. We use the data as input, and we standardize it by PA, that stands for presence absence. So every time a species is present in a site, the values are converted to 1, and if it's absent, it's nil. So now we can simply calculate the sum of occurrences of each taxon by using the data. In the apply function, 2 stands for the columns over which the function is calculated, and the function that is used is the sum. So we calculate the sum, we sort this, and we see that some species only occur 3 or 4 times, whereas others occur in all sites. And we decide to remove the rarest species. So this is done with this function. We select all species that have sum of occurrences below 5, and we remove them from the data set. In the next step, we check for the range in the species abundances, and we see that some species only have very low fractions of occurrence, or they only occur very low abundances. That's probably the coverage of some in percent of some habitat patch that has been monitored or something like that. We can treat this as abundances here as well as mean abundances. It doesn't really matter in this case. What we see is generally that we have a large variation in the maximum values and in the variation that is related to the species. That would mean that the species with the highest abundances would dominate the variation, and would be, if we would run a redundancy analysis, the major variance would be that of the highly abundant species. So we would mainly focus on these if we don't standardize the data. So we can do the standardization directly within the RDA command, so we don't need to do this in advance. Now we load the chemical data. This is chemical data from the soil in which the lichens have been sampled from. So we see here that there are different ions that have been measured from aluminium, iron, and so on, but also habitat, percentage of habitat that is covered. It's the bare soil variable, the depth of the humus, and the pH. As for the multiple linear regression analysis, collinearity may influence our results of the RDA, so we need to account for that, and we do this, and you know this already from the context, in the context we've done this already, of multiple linear regression analysis. We use this pair function to first look to visualize pairwise relationships between variables, and when we look at that, here we see that several of the variables have relatively high relationships. For example, sulfur and potassium. We have magnesium and calcium that have a relatively high relationship, and phosphorus also correlates strongly with several of the ions. We can look at the remaining variables. Here we don't see that high variation except for the pH and the depth of the humus layer. So we now remove, and that's basically just an arbitrary choice, not completely arbitrary, but let's say we would be lichen specialists and we remove calcium and potassium, because we would know that they have not such a strong effect and other variables are much more important. So after we have removed these variables, now we plot again. We check again the correlations between variables, and we see that there are still some some correlations that are relatively high. For example, between aluminium and iron. We could theoretically, omit iron or aluminium. We decide here to omit iron, as it's known that, especially as low pHs, that aluminium is toxic, and has been one of the causes of toxicity in the context of acid rain and the bioavailability of certain aluminium ions that are toxic to the flora. So we remove iron, so we expect that aluminium is more important, and then we calculate the variance inflation factor. So that's all the same as for multiple linear regression analysis. When we look at the factors, we see that we still have some variance inflation factors that exceed thresholds given in the literature. For example, a threshold of 10 is given in Borchardt et al., and other textbooks values of 5 are given. Since we are no complete specialists, and for us it doesn't matter whether a variable that is collinear yields to a more spurious relationship, that's not of our main interest here. So we keep all remaining variables. Now we check the length of the gradient. Remember that in RDA we look for a linear gradient. So if we have less than 2 standard deviations or up to 2 standard deviations, then we assume that the gradient is still linear. If we have 4 standard deviations, we expect a full turnover and the unimodal gradient. We calculate the grana and we see that generally, except for the first axis, that most of the axes are below 2 standard deviations, and it might be appropriate here to use the RDA. We can also see that if we would Hellinger transform the data and have a look at Hellinger, the Hellinger transformation has been suggested as one that is appropriate for species data in linear analysis using RDA. That this would decrease the gradients further. So if we look now at the gradients, we see that the length of the axis has decreased, and they are all clearly now below 2. So Hellinger transformed data would otherwise contribute to shrinking the length of the axis. However, if we use transformed species data, obviously the interpretation is more difficult than if we use the raw data. So since we are relatively close to the 2 standard deviations, we keep the original data and we conduct the RDA. The RDA is simply done using the RDA command, as we have done before in the context of PCA. Here we use the formula notation that is known to us from the context of multilinear regression analysis. So we have the formula notation says that the species data as explained by all environmental or all explanatory variables, that's indicated by the point, and scale equals true means that the data is standardized before, so centered to mean of 0 and to a standard deviation of 1. So we run the RDA and we have a look at the summary that we obtained out of this RDA. So what we see here is first the formula, then we have the partitioning of the variance of the RDA as explained in the lecture. So we have, on the one hand, we have the variance that is explained by the variables, that is the constraint variance, and then we have unexplained variance in the data set that is not, so the variance that is not captured by our environmental variables. And that's about 47% of all variation. Then we have the eigenvalues, and we see here that the eigenvalues, the proportion explained, relates to the total variation. So if you wanted to know the amount of constraint variance that is explained by the individual axis, then you would recalculate this. Or we can roughly, in this case, we have roughly 50% that is explained variance and 50% that is unconstrained variance. And we could simply multiply by 2 the proportion of constraint variance. On the first axis would be about 25%, and so on. So we have the importance here. So the number of RDA axis is quite obviously the number of explanatory equals the number of explanatory variables, unless we have some fully collinear explanatory variables. And then we have the remaining, for the remaining number of axes is here the PC axis, because that's basically principal component analysis that we have discussed before. So we see here here's actually the proportion of explained, only the explained variance given for the, so we don't need to calculate this by ourselves. So then we have species scores, where the species are positioned along the axis. We have site scores, and we have site constraints, that are the fitted values in the sites, and we have b-plot scores for the constraining variables. So we could repeat this whole analysis, including the rare species, and would find out that the total constraint variance is higher, but that the explanatory power on the first axis is lower, which basically means that additional species that enter the analysis are not explained by the main gradients. We could extract the canonical coefficients using the coefficient function coef, and then we check the RDA result. We check whether the full model is statistically significant, so that contains all variables, if you remember, and we see that this is not, in the permutation test, is not statistically significant, although a p of 0.08 is not very far away from 0.05. For the canonical axis, we can also run a permutation test. This permutation test is described in more detail in this paper that is given here, and it provides us with information on the statistical significance of the individual axis. Now we plot the data. And first we use scaling 1. We use the weighted average scores. That means the species are plotted as averages of the sites. So in fact I replot the proper size. So now we have a better visualization of the environmental variables. I don't go into details here, but what you can see here are the sites, are the environmental variables, and the species. And when you project the species along the environmental variables, or the sites along the environmental variables, you can estimate to which extent the environmental variables, which values they have in these sites. And in addition, you can see to which extent the individual variables contribute to the major gradient axis. You can see this along the first and second axis. And what you can also see is that here the correlation coefficients can be read on the axis via this, from this scale, this provided on the right hand side. And you can see, for example, that manganese has a relatively high correlation with the second axis. So here are a couple of more information on how to interpret this plot. I'm not going into details here. we move on to the correlation tree plot that rather provides information on the relationship between the different variables. So here in this correlation tree plot, the scaling of the results of scores and so on leads to has the effect that we can't really identify species names anymore. They're all plotted above each other. But now the angle between the variables and the angle to the sides and between species indicates the correlation between environmental variables and between sites. You can also see that generally the angle is not that different between the two types of scaling. So while it's more precise to use scaling 2 to evaluate correlations and should generally be done, we see that even under scaling 1 we don't have such a big difference in the display of data. So here's some more text that you should read. You could also look at LC scores. So these are the scores of the linear predictors. These are the fitted scores, but I don't run through this here. And finally, we could use RDA and model building. So if we don't know which, like in multiple regression analysis, which variables should be included, we have the option in the vegan package to use the adjusted R square in model building. So the formula notation is the same as before. We start with a model that contains only aluminium. We give the scope of the step function to the full RDA object so that we have fitted before. That's the object that contains all variables. And we run this function. And we see that we end up with a model that contains aluminium, phosphorus, bare soil, and nitrogen content of the soil. So we fit this model. And we see that this model explains about that our variables explain about 25% of or 23% of total variance. These 4 variables. That doesn't sound like much, but if you imagine that many environmental variables influence communities as well as intraspecific interactions and are not taken into account here, then that is not too bad. So we test statistical significance again and see that now the model is significant. We also test for the individual axes. We see that still only the first axis is significant. If we calculate the variance inflation factor for this model, we now see that all variance inflation factors are below 1 and thus okay. So we plot again this final model. So this is our result of the analysis. That would be the result. So we expect that these 4 variables are the main drivers, and we see from the length of these plots, and we probably plot that again, we see from the length of the individual arrows that particularly the phosphorus, aluminium and bare soil contribute much to the positions of the species in the sites, as long as we can interpret the correlations as causal. Finally, we have the issue of partial RDA. So let's say we are interested in the pure effect of bare soil. We want to remove the effect of aluminium, phosphorus and nitrogen, then we can rerun the RDA and use this condition part in the function. That means after we have removed the aluminium, phosphorus and nitrogen, we are interested in the pure effect of bare soil, and we obtain different set of information what we obtain for this condition. It's already too far to scroll down a little bit. We get the conditioned variance of the total variance, so we see that a major part of the variance has been explained by the variables that have been removed, and the constraint variance, that the variance that is explained by the bare soil after, so it could be interpreted as habitat variable after the other variables have been the influence of the other variables has been removed, is about 6%. We obtain eigenvalues and for constrained and unconstrained, and species scores, and so on. We can plot this. So we now obtain information on the relationship. Bare soil is here the only variable in the model, so it's directly along the first axis, and we see that the second axis is a principal component axis. And now we could interpret the relationship between the species and the habitat variable bare soil. So that's it regarding RDA. In the exercise, you should run an RDA on your own using the RIGS dataset. Have a look at Sur et al. To know more about the data, and a little bit more description is provided here in the script. That's it for RDA. I hope you enjoyed the session and you now are able to go through an RDA yourself.